Okay, so here is our summary table of the common nucleophiles and their relative reactivity. Again, just to summarize our rules for nucleophile strength. 1, we look at atomic charge. So the negatively charged atoms are more nucleophilic than your neutral atoms. Next, you look at atomic size, where your large atoms are more nucleophilic than your small atoms. So the classic example is sulfur-based nucleophiles are more reactive than oxygen-based nucleophiles. The next thing we look at is hindrance. So hindered, bulky bases will act as bases rather than nucleophiles. So for example, if we compare T-butoxide functions as a base. Well, for example, methoxide is more readily able to function as a nucleophile because it has less steric bulk. The final effect that we'll look at, or that we observed, were resonance effects. Delocalized lone pairs are less nucleophilic. So for example, if we look at acetate, acetate's lone pair is much more delocalized than, for example, methoxide, because acetate's lone pair can be delocalized across multiple atoms via resonance. Okay, so now that we have the idea of what makes a strong versus a weak nucleophile, let's talk a little bit about the leaving group. So this is the species that's kicked out in the reaction. So in general, a good leaving group is a weak base and a weak nucleophile. Okay, so a wonderful tool. Remember that pKa table I gave you all the way in chapter 2? Well, it has another use. It has another use. Weak bases are excellent leaving groups. So you may want to memorize and just be familiar that all of your halides and tosylate, which is abbreviated as OTS. What is tosylate, you may ask? It's toluene sulfonic acid. So you have a toluene part and then a sulfonic acid part, or otherwise known as tosic acid. So halides and tosylates are great leaving groups, and they're very weak bases. So you can use base strength as a tool to assess how readily and how good of a leaving group is. Now, water is another good leaving group, but I just want to put a star next to water. Water typically only functions as a leaving group under acidic conditions. You will typically only see water leave under acidic conditions in most cases. Now, there's one exception. Remember when we talked about it last time? But fluorine is an extremely poor leaving group. The carbon-fluorine bond is very strong. So fluorine doesn't react like typical halides. It's not easily displaced. So if you see reaction conditions for a reaction where we're trying to displace fluoride, nothing will happen. This is a common trick question that they put on some ACS exams. If you see fluorine in a displacement reaction, nothing will happen. Carbon-fluorine bonds do not react readily in substitution or elimination reactions under the conditions we'll talk about in this class. Now, in terms of your moderate leaving groups, you have your acetate and your ammonia. Your poor leaving groups are strong bases. And when you hear the word extremely poor leaving group, these almost never leave. So these extremely poor leaving groups will almost never leave. So when you think about product prediction, you're very unlikely to ever kick out these anionic, extremely strong bases. You're never going to kick out alkyl groups in most substitution displacement reactions. Does this table make sense to everyone so far? Again, you can think back to the rules to what governs strong acids, what governs weak acids, what governs strong bases and weak bases. And depending on the strength of the base, you can determine whether something's a strong or weak leaving group. Okay, so all of this information is present in tables. Now let's talk a little bit about properties and strategies involving leaving groups. So a good leaving group must accept a negative charge easily and stabilize a negative charge. The leaving group must be bonded to an sp3 carbon for SN1, SN2, E1, and E2 reactions. So your vinylic species and your aromatic leaving groups are not typically reactive under SN1 substitution and elimination conditions. Or if they do undergo substitution or elimination, they go through entirely different mechanisms. So if I have to summarize all these tables, good leaving groups are weak bases that can stabilize and delocalize electron density. Now, of course, we're not always going to have the perfect leaving group. So sometimes we have to prepare a leaving group using chemical reagents. So often a poor leaving group is converted into a good leaving group via activation. So some activating agents are thionyl chloride, phosphorus tribromide. And in these methods, we take our primary and secondary alcohol, we activate it by generating a chlorosulfite or a dibromo phosphite. And then once our leaving group is activated, then our nucleophile can attack and displace our leaving group. So let's just draw out our leaving group. Let's just draw out our leaving group and let's look and see. Is the anion generated? Is this leaving group that we kicked off, is this anion stable or unstable? Is this anion relatively stabilized or destabilized, looking at this structure? It's relatively stabilized. You can kick it and delocalize it through multiple atoms, and it's attached to multiple electron withdrawing groups. That's pretty good. Now, one nice benefit of these phosphorus reagents is that the phosphorus oxygen bond is relatively stable. And you can even stabilize it further via resonance and forming this relatively strong phosphorus oxygen double bond. So we have almost a thermodynamic sink of sorts. Yeah, so we have a highly stabilized leaving group in both of these processes. Another method that you'll see for activation is generation of a tosylate or a mesylate. So suppose you have an alcohol you can treat it with a generic base such as triethylamine. Probably in terms of generic bases, let's just use sodium hydride to make the mechanism easy. And then you treat it with toluene sulfonyl chloride, otherwise known as tosyl chloride. You end up with a substitution, and you generate your activated tosylate. So this is abbreviated as OTS. Whoops. One moment. And then you can do further chemistry. Reaction with nucleophiles for these tosylates occurs much more readily. This is another very common method of activating alcohols that you'll see throughout the chemical literature, generation of a tosylate. Does this make sense to everyone? Does everyone understand the logic behind activation? We're generating a more stable leaving group. And in general, the way that we do that is by attaching on an electron withdrawing functionality to our leaving group. Any questions so far? Okay, let's keep going then. In terms of the solvent, so for SN2 reactions, a higher energy nucleophile, I want you to think less stable nucleophile, generally results in a faster reaction rate. So polar protic solvents, I'd like you to think hydrogen donor and H bond acceptor solvents slow SN2 reactions by stabilizing the nucleophile. How does this work, you may ask? Let's suppose we're dealing with an alkoxide. Well, our solvent could just as easily surround the alkoxide. So if it was run in, for example, an alcoholic solvent, we'd end up forming hydrogen bonds that stabilize our nucleophile. Now, polar aprotic solvents that lack hydrogen bonds form weaker interactions with the substrate, and they permit faster SN2 reactions. So for example, in this reaction where they're generating an azide compound, depending on your solvent used, so looking at methanol and water, these solvents are they protic or aprotic? Looking at methanol and water, are these solvents protic or aprotic? Protic or aprotic? And don't be shy to type in the chat. Protic, yep. These are protic solvents. And as we notice, protic solvents have a slow rate. As we move towards aprotic solvents, these are the big three aprotic solvents: dimethyl sulfoxide, dimethylformamide, and acetonitrile. These are all wonderful solvents for polar aprotic reactions. HMPA, I'm just going to put a star next to. HMPA is a little bit special in that HMPA is also really wonderful for activating anions and nucleophiles. Hexamethyl phosphoramide, it's not a fun solvent to use because it's hard to remove and it's relatively carcinogenic, but it's really wonderful for activating anions and nucleophiles, just in case you were curious. Okay, just to provide you a structure, here are some common polar protic solvents that you should know and you'll be tested on. And here are the common polar aprotic solvents. Any questions so far? So again, polar aprotic solvents permit faster SN2 reactions. So let's write that down. So polar aprotic, we have a faster SN2. Polar protic, we have a slower SN2 reaction. So depending on your solvent choice, you can skew which reaction pathway is accelerated and which reaction pathway is preferred. So solvent has to be chosen very carefully. Now, to talk a little bit more about polar protic solvents can interact with nucleophiles and electrophiles, and they can undergo hydrogen-like bonding with the nucleophile. Now, this in turn stabilizes and weakens our nucleophile because the lone pair, this nucleophilic lone pair, is participating / stabilized by a hydrogen bond. So hydrogen bonding stabilizes our nucleophile, which makes it less reactive in substitution reactions. Polar aprotic solvents cannot undergo hydrogen bonding with nucleophiles, and as a result, we end up with a more localized charge, which in turn leads to a generally more reactive nucleophile. Okay, so this is the rationalization for these different solvent effects. Let's talk a little bit about how all of these effects tie into our energy diagram for each of these different reactions. So looking at the SN2 reaction coordinate, we have our reactants, we have our transition state, and we have our products. So again, the rate of reaction depends on the concentration of the nucleophile and the substrate. So this is a bimolecular reaction that it occurs in a concerted single step. As we can see in the energy diagram, only having one transition state. Now, what else do we notice about this reaction? What else do we notice about this reaction? Is it exergonic or endergonic? Yeah, so this is an exergonic reaction where the transition state depends on reactant. Well, another way to phrase this is that we have a reactant-like transition state. So the characteristics of our reactants heavily affects the activation energy and the relative energy of our transition state. Now, just a few things to note. The activation energy depends on the nucleophile and reactant energy. Activation energy increases as substrate substitution increases, where tertiary is greater than secondary, greater than primary. In terms of activation energy, remember the higher activation energy, the slower the reaction. Good leaving groups result in a lower activation energy, and the exact product energy depends partially on your leaving group, whether your leaving group is stabilized or destabilized, whether it's a good or a poor leaving group. Okay, let's now dissect this reaction diagram a little bit, and let's talk about the effect of steric hindrance. So as our substrate hindrance increases, the activation energy increases and our rate decreases. So just to rationalize what's going on here, so if we look at a primary species, and our nucleophile is trying to approach, and we compare that to a secondary species. Let me draw the transition state. Allow me one moment to do that. And if we compare a primary substrate to a secondary substrate, we see very clearly that the secondary substrate has a greater amount of steric interactions. So steric interactions result in a higher energy transition state. So the more hindered your substrate, the greater your activation energy and the slower your reaction. So this explains why primary and secondary carbons react more readily via the SN2 reaction. This also explains why bulky nucleophiles have slow or negligible reaction rates. Looking at nucleophile energy. So as nucleophile energy increases, if you have a good nucleophile, your activation energy decreases. So to talk a little bit about why that is, so if we look at our nucleophile here, and we think about our transition state, where we have our nucleophile attacking, and we have this transition state where our nucleophile is forming a bond with our desired carbon and our leaving group is leaving. The nucleophile energy in the transition state and in the reactants doesn't change substantially. However, the higher energy your nucleophile is, so let's suppose we have a high energy nucleophile or a stronger nucleophile, the smaller your activation energy required to reach the transition state becomes. So essentially, the better your nucleophile, the higher energy your nucleophile, the less energy is required to reach your transition state. And in other words, the lower your activation energy. And that's mostly because regardless of whether you have a good or a poor nucleophile, your transition state energy won't change substantially as you change your nucleophile's strength. There is some variation, but the relative energy of your nucleophiles is a much greater effect in terms of the rate of SN2 reaction. So good nucleophiles are high in energy and are less stable than poor nucleophiles. One thing that I do want you to note is that acid-base reactions can compete with substitution. So if you get to these really high energy nucleophiles, you can sometimes see competing acid-base reactions at play. Does this make sense so far? Do these energy diagrams make sense so far? Any questions so far? Again, we could tell that the SN2 reaction occurs in a single concerted step. because we only see one transition state in this energy diagram. Okay, so let's talk about our leaving group. So good leaving groups result in a lower activation energy. So if we think about our transition state, in our transition state, we are breaking a bond with our leaving group and forming a bond with our nucleophile. From this information, we can see that better leaving groups. So if we have a better leaving group, would it take as much energy to reach this transition state where we're partially breaking this bond to the leaving group and partially forming a bond with our nucleophile? If our leaving group is good, will it be easier or harder to reach our transition state? If our leaving group is good, it's easier to break this bond. It, of course, would be easier to reach the transition state. So better leaving groups have a lower activation energy. Okay, so let's keep going. Let's talk a little bit about polar protic solvents. So as a refresher, polar protic solvents stabilize the nucleophile, the energy decreases, resulting in a larger activation energy and a slower reaction rate. And we've seen and we've discussed the reasons behind this previously. Note, the transition state energy is about the same in both solvents. The solvent affects nucleophile energy. So the solvent is affecting the relative energy of our nucleophile to this transition state. It's not influencing as much our transition state. Does that make sense to everyone? Looking at the graph, does everyone see how the transition state energy is about the same, but our reactant energy, our relative nucleophile energy, is quite different depending on the solvent? Does this make sense to everyone so far? Okay, perfect. So let's take a look at two reactions and let's try to draw a reaction coordinate comparing these two reactions. So let's look at these two reactions and I just want you to tell me the difference between these two reactions. So we're clearly dealing with an SN2 reaction. So both these reactions are an SN2 reaction. And I'd just like you to tell me what is different. What have we changed in these reactions? What have we changed in these reactions? They're both SN2 reactions. But let's look and let's go through each of the pieces. So first, let's check our substrate. Is there any difference in our substrate? So I see in the chat, someone mentioned the solvent changes. Yes, that's correct. But to help proceduralize this, we look at our substrate. The substrate's the same. Then we look at our nucleophile. Our nucleophile is the same. Then we look at the solvent and we see that our solvent is different. So let's label these reactions. So looking at reaction A, acetonitrile, CH3CN. Is that a polar protic or polar aprotic solvent? Is that a polar protic or polar aprotic? Is it polar protic or polar aprotic? Don't be shy to go to your reference table, but just looking at this structure as drawn, can this structure form hydrogen bonds? It's aprotic, exactly right. Okay, perfect. Technically, fully, it's polar aprotic. Now, if we look at acetic acid, CH3 with our carboxylic acid, is that a polar protic or polar aprotic? Is it polar protic or polar aprotic? Acetic acid. Can it form hydrogen bonds? Yep, it's protic. Okay. So then, when I draw my picture, okay. So we're looking at polar protic solvents for B. And for A, we have a polar aprotic. So then, what changes when we change our solvent? What changes? So we have our reactants, we have our transition state, and then we're looking at our products. So what changes when we change our solvent? What changes when we change our solvent? The reactant, transition state, or product energy? Which one of these do I change? Which one of these is going to change when I change my solvent? Wait, going back to the solvent, what changes when we change our solvent? Is it the reactant, transition state, or product energy? So looking at our discussion of solvent effects, the change of solvent when you go from polar protic to polar aprotic primarily affects your reactant energy. So for example, for our polar protic solvent, we draw it as relatively low energy. We go up to our transition state. Oops, let me adjust this. Low energy. We go up to our transition state and down to our products. For a polar aprotic solvent, the aprotic solvent is, now if we compare aprotic to protic, should my aprotic be higher or lower energy? Are my reactants higher or lower in energy when we have an aprotic solvent? Is our reactant going to be higher or lower in energy? For aprotic solvent, you're exactly correct. It should be higher in energy. So here's our aprotic solvent. The transition state has about the same energy, and our products have about the same energy. So the main difference when we change our solvent is that our reactant energy, our nucleophile energy, changes. And as a result, the activation energy for our aprotic solvent is less than the activation energy for our protic. Does this problem make sense to everyone? So in a step-by-step guide, you look at both of your reactions. You look at your substrate, your nucleophile, your solvent, and you also look at your leaving group. Then you compare, you find the difference. We found it was a difference in solvent. We identified we have a polar aprotic and a polar protic solvent in these two reactions. We know that polar aprotic solvents have higher energy nucleophiles. The aprotic solvent is less readily able to stabilize your nucleophile, and as a result, has a lower activation energy. The transition state and product, when you change your solvent, the energy doesn't change substantially for your transition state and your products if you have the same reactants. Does that make sense to everyone? Does this idea of drawing reaction coordinates make a little bit of sense to everyone? Okay, so let's now try with a different example. So comparing the following two reactions, I'd like you to identify the major difference and then try to draw a reaction coordinate comparing these two reactions. And I'll just make some space. So there's some space below for you to try using the annotate feature to draw a reaction coordinate. Let's focus for now on trying to identify the major difference between these two reactions. And I'd like someone to break out and try using the annotate feature to draw a depiction of the reaction coordinate for each of these reactions. Yep, someone's already saying it in the chat. We have a difference in nucleophiles. I'd like us to take a few moments, and now that we're comparing our nucleophiles, we have ethane thiol versus acetate. And I'd like you to try and draw out, using the annotate feature, a reaction coordinate comparing these two compounds. So if we compare our nucleophiles, how does nucleophile strength affect our reaction coordinate? So let's take about 2 to 3 minutes to try to draw out a sketch, and I'll label ethane thiol as A and acetic acid or acetate anion in this case as B. And I'd like you to draw two reaction coordinates, one for A and one for B for these displacement reactions. I mainly want to see if you can think through how changing different reaction parameters affects your activation energy and your reaction rate. So let's take about 2 to 3 minutes and try to draw a reaction coordinate using the annotate feature, and then we'll come together as a group to discuss in about 2 to 3 minutes. So you're on the right track. You're very close to the right track in terms of the key difference between A and B. So looking at this chart, the proposed drawing indicates that nucleophile B is higher in energy. So if we compare ethane thiol and acetate, I'd like everyone to chime in. Which is the stronger nucleophile? Ethane thiol or acetate? What is the stronger nucleophile? What is the stronger nucleophile? Ethane thiol or acetate? Ethane thiol, right? We're comparing a localized sulfur-based nucleophile to a delocalized oxygen-based nucleophile. So we know that ethane thiol is a stronger nucleophile, and ergo, is it higher or lower in energy? If ethane thiol is a stronger nucleophile, is it going to be higher or lower in energy? Higher, yep. So then, just to clear the annotation, And I see in the chat that you communicated that you had them, that you accidentally flipped them. That's more than okay. I'm glad that you recognize that it was a difference in energy. Yep. So the higher energy the nucleophile is, the faster your reaction. That's exactly right. And we'll talk about that in a moment, looking at our two reaction coordinates. Okay, so here is B. Now let's look at A. So A, we have a higher energy nucleophile, and as a result, if we think about our activation energy, the activation energy for reaction A is less than the activation energy for reaction B. In other words, what we've been saying all along, stronger nucleophiles react faster via SN2 pathways. Exactly right. The higher in energy your nucleophile, generally the faster your SN2 reaction. Does this make sense to everyone so far? Is everyone comfortable with these trends? This is trying to make explicit a lot of the implicit reasoning that we use when we say, oh, this reaction's faster. The reason why stronger nucleophiles react faster is the nucleophiles are higher in energy, and as a result, the activation barrier is lower. Okay, let's keep going. Let's look at one other example. So I'd like you to take a moment and I'd like you to tell me together, what is the major difference between these two reactions? Let's take about a minute to think about that. What is the major difference? Okay, perfect. So looking at reaction A, what is our substrate? Primary, secondary, or tertiary? Substrate A is primary, okay. And what about substrate B? What about substrate B? Secondary, yep. Okay, so let's think a little bit about substrate effects. So when we think about substrates, what does the substrate change in our reaction diagram? So if we have our reaction diagram and we're looking at our reactants, our transition state, and then our products. What happens when we change and we look at a primary versus secondary? So fundamentally, we're looking at a primary versus a secondary substrate. What's going to change in our reaction coordinate? The reactant energy, the transition state, or the product energy? What is most affected when we start changing substitution? The transition state, yep, exactly right. So for primary, our reactants are relatively low in energy. Our transition state is a relatively small jump, and we generate products. For a secondary substrate, our reactants are a little bit higher in energy, but our transition state is substantially higher in energy. So if we compare our activation energy, the activation energy for a secondary substrate is substantially greater than the activation energy for a primary substrate. Does that make sense? There's a small difference in reactant and product energy, but the main thing I want you to focus on is the activation energy. Because if we look at and we compare a primary and secondary substrate transition state, we'll see very clearly that for the primary substrate, we don't have a ton of steric hindrance. While for our secondary substrate, we have another substituent that adds to our steric hindrance and raises the activation energy and raises the relative energy of our transition state. So the main thing that changes when we change our substrate is that activation energy increases as substrate becomes more substituted. Ergo, primary reacts faster than a secondary substrate because the activation energy is smaller. Does that make sense to everyone? Does this trend make sense in terms of substrate effects? Okay, so let's keep going now. And let's look at a mechanism example. So this is a nice case where we can begin to tie together and begin to think about the key features of SN2 reactions. So I'd like you to take a moment. and look at the following compound, which is one conformation of this compound shown here. Iodocyclohexane. Now, my question to all of you is, first and foremost, what is the mechanism for this reaction? I'd like you to draw a mechanism and predict the products. And I'd like you to tell me which chair conformation is more reactive. Well, let me put our dash wedge representation over here. And we know that this chair conformation is just one of the possible conformations for this compound. So the other possible conformation looks a little bit like this, with the iodine in the equatorial position. Now, what I'd like you to tell me is after drawing out all of the hydrogens, I'd like you to tell me which conformation is more reactive. And I'd like you to draw the products in dash wedge notation and as a chair conformation. Let's take about 3 to 4 minutes to try and work through this problem. I'd like at least 1 to 2 students to try to propose a solution to this problem using the annotate tool, and then we'll discuss this solution together as a group in about 3 to 4 minutes. So let's take a few minutes and work through this problem and try to draw out our proposed solutions. Really try to look at a model of each of these chair conformations, and I'd like you to tell me fundamentally whether the axial iodine or the equatorial iodine is more reactive in the SN2 reaction. So don't be shy to break out the annotate tool and try to predict and draw the products from this reaction. And I'll be making a model for our discussion in approximately 3 minutes. But I'd like to see a few responses using the annotate tool before we discuss in detail. And don't be shy to message me with questions. I just want to give everyone some time to think through this problem, make a model, and try to see which of these conformations is more reactive in the SN2 reaction. But don't be shy to break out the annotate tool and propose your solution. We'll discuss in about 2 minutes to 1.5 minutes. Don't be shy to propose your solution. It would be a great starting point for the discussion. We have one student proposing that the axial position is more reactive. Okay, that's that. So are there any other responses? Would anyone like to draw out the proposed product from this reaction? What's our nucleophile going to be? DMSO, which is the solvent, or cyanide? Cyanide, yep. So cyanide's going to function as the nucleophile. And instead of attacking the iodine, which is our leaving group, it's going to attack the carbon that the leaving group is attached to. So let's talk about this problem as a group. And I already see some interesting proposals in the chat. So first and foremost, from a mechanistic perspective, the cyanide will attack the carbon that the leaving group is attached to, and your leaving group will leave. In turn, this results in an inversion of configuration. So now instead of having your cyanide in the axial position, your nucleophile, which is cyanide, is now in the equatorial position. This is the equivalent of the following dash wedge depiction. So as we notice, we have an inversion of configuration. Now to answer the question, what chair conformation is more reactive? Let's look and let's entertain both of the possibilities for our chair conformations. So, oops. Okay, so here is our first potential chair conformation. This is the exact same chair conformation as shown here. Now, in terms of how we can displace our leaving group, I'd like you to pay special attention to our hydrogen atoms. Let's pay special attention to our hydrogen atoms. So if our nucleophile tries to attack when it's in the axial position, we have a nice clean approach where we aren't necessarily bumping into many hydrogens. Does everyone see how if we're trying to attack this back carbon, there's a nice clean approach from the back side of our leaving group that doesn't bump into a ton of hydrogens? Does everyone see how this approach is relatively unhindered for the axial position? Does that make sense to everyone? So here's our axial iodine. We can attack from the backside with minimal steric hindrance. Can everyone see that in the camera? Does everyone see that when we play with the model kit? Now, if we undergo a chair flip, and we entertain our second possibility, which is shown right here, you may think, oh, not much has changed. But my question to all of you is the backside of our iodine on the bottom, or is it on the, which side is the backside of our iodine? Is it on the bottom, or is it on the inside of our ring? Is it on the bottom or inside our ring? Where's the backside of our iodine? Where is that sigma star? It's more on the inside. Now, you may say, what's the big deal about that? Well, let's look at the approach. If we are trying to attack behind, so here's our approach if we're trying to attack behind our iodine. So if we're trying to attack behind our iodine, we bump into multiple hydrogens. There are 3 axial hydrogens that block our approach. Again, just to show this from the side, once again, if we try to attack our iodine, there are multiple axial hydrogens. So is this attack easier or harder to do when our substituent's in the equatorial position? Are we bumping into more things when we try to do an SN2 on an equatorial position? It's harder, right? So from this discussion, so let's just draw what's going on here. So our nucleophile is approaching, and when it's axial, it has a very easy approach. When our nucleophile is approaching at the equatorial position, the equatorial attack is more difficult. Why? Because geometrically, to attack the backside, to attack our sigma star, we'd have to bump into 3 axial hydrogens in our approach. Does this make sense to everyone so far? Does this idea make sense? So we're looking at the geometry of our SN2 reaction. To answer the question, how do you know to add cyanide with the dash notation? Remember, for an SN2 reaction, does it occur with retention or inversion of stereochemistry? SN2 reactions, do they occur with retention or inversion of stereochemistry? Would the class like to chime in on this matter? This is a really critical portion. Yes, SN2 reactions occur with inversion. of the stereocenter. So just to showcase that, if we're looking at our axial species, oops, let me get this up to the camera. One moment. Here we go. So here's our axial species. So when we attack our axial and displace our leaving group, we attack our carbon and displace the axial iodine. The stereocenter undergoes an inversion. And now our substituent ends up at the equatorial position. As we can clearly see, is our newly installed nucleophile axial or equatorial? Is our newly installed nucleophile axial or equatorial? Equatorial, yep. We can clearly see an axial hydrogen in our equatorial substituent. So this is a two-part question. One, it highlights that axial substituents are more reactive in SN2 reactions. And it highlights that SN2 reactions occur with an inversion of your stereocenter. Just two things you always need to have in the back of your mind when I ask you to predict products. You need to show the proper stereochemistry for your products. Does that make sense to everyone? Does this make sense so far? Perfect. So let's keep going now. And I'd like you now to take and have a try at the following problem. So this is another example where you have to be very careful when drawing your product and showing the proper stereochemistry of your product. So given the following reactant, I'd like you to draw the products of this reaction in both Newman projection style and dash wedge style. So I'll give everyone a few minutes to make a model. I'd like to see a dash wedge depiction of the following molecule, as well as the dash wedge and Newman depiction of the product for the following SN2 reaction. And remember, this is representing acetate, which looks something like this. So let's take 4 to 5 minutes to work through this problem, and I'll be making a model in the meantime, and then we'll come together as a group to discuss. Predicting the products from a reaction with the correct stereochemistry is a critical type of question and a critical skill that you'll need to develop in this chapter. Especially with these Newman projections. We're going to be doing a lot of Newman projection analysis in this chapter. And don't be shy to break out the annotate tool and draw the reactants and products in dash wedge and Newman form. If not, we'll discuss in about 3 minutes. And don't be shy to message me questions from this problem in the chat. I'm just checking that everything's functioning on the camera. Oh, I have it reversed. One moment. And don't be shy to make a model and draw out your proposed structure using the annotate tool. Any questions so far? We have about 2 minutes until we start our discussion. I'd like to see at least 1 to 2 responses in the chat or using the annotate tool for this problem. Yes, yes. So I want to see both a Newman projection and a dashed wedge chain depiction. But whatever feedback you provide using the annotate tool, I'd be happy to look over for our discussion. Oh yeah, that's one way of depicting this molecule in dash wedge. It looks good. Looks good. Yep. Would someone else like to volunteer to depict the product, or would the same student like to volunteer to depict the product in either Newman form or dash wedge form? Yep, that looks fine so far. Oh, and you're even drawing the mechanism. Perfect. And what would this look like after SN2 reaction? How would we draw our product in the Newman projection? Keeping in mind that the acetate is attacking from the back side of the bromine. And SN2 reactions occur with an inversion of configuration. Yeah, yep. Or you can draw it where the acetate is pointing down and one of the methyls is pointing up. That's another way of drawing it. Yep, both are fine. Yep, exactly. So we've inverted that center. Essentially, anytime you have an inversion, you swap the position of two substituents on your carbon. Well, it is relevant because the two different stereoisomers are non-superimposable, right? And because that is a stereocenter, it changes the chirality. Yes, exactly right. Just as we discussed last time. So this has been wonderful so far. I really like everyone's dash wedge depiction and Newman depiction. Would someone like to convert the Newman projection depiction shown into dash wedge notation, keeping in mind that this reaction has occurred with the inversion of stereochemistry at our stereocenter? Would someone like to provide the last finishing push for this problem? And then I'll provide the instructor solution. Yep, the stereochemistry is perfect. And I greatly appreciate the fact that you drew the ring and you drew your straight chain exactly like your starting material. So that way there are no issues with rotation. Perfect, perfect. So I've seen a lot of wonderful responses so far. So what I'm going to do now is I'm going to clear and I'm going to provide an instructor solution. So in terms of mechanism, the SN2 reaction occurs with a backside attack on the carbon that our leaving group is attached to. Okay, so to draw out this structure and convert this Newman projection into dash wedge projection, first things first, I'd like you all to stare at the following structure and I'd like you to tell me, does this match the Newman projection? Does this match? Sorry, one moment. Okay, does this match the Newman projection picture that we have? So we have our bromine up top in the front, our methyl on the left in the front, our hydrogen on the right in the front, our hydrogen on the left and on the bottom, and our methyl on the right. Okay, now here's the trick. Remember when I taught you the zigzag method? We have a nice zigzag chain. So all we're going to do is we're going to take our structure and we're going to turn it 90 degrees. So now we have this nice zigzag chain and we're just going to draw what we see. We're just going to draw what we see. Okay, so I'm going to draw my chain exactly as I see in my camera. And now my question to you is this hydrogen pointing towards or away from us? Is this hydrogen pointing towards or away from us? Towards, yep. So we'd give it a wedge. And is the bromine pointing towards or away from us? Away. So the bromine gets a dash. Okay, so if we're drawing the attack of our nucleophile, our nucleophile is going to attack from the back of our bromine. So thinking about the back side of our bromine, if our bromine is all the way in the back here, the back side would be an attack. Is this the front face or is this the back face? So like relative to us, if I put this nucleophile right here, would the nucleophile be towards or away from us? Would it be towards or away from us? Is this blue sphere, which is our nucleophile, it's pointing towards us, right? Okay, so the attack occurs. And the way I represent inversion is I take my leaving group off, I take my hydrogen, and I swap its position. Then I put my nucleophile on, and then I draw what I see. And after the displacement, after this displacement, in terms of our products, we're going to draw our chain exactly as we see it. So the same zigzag pattern that we see. Now, is our nucleophile, is our acetate pointing towards us or away from us? Is acetate pointing towards or away from us? Towards. So what symbol do we give it? A dash or a wedge? If it's going towards us, towards us. What symbol? Yep, it gets a wedge. Exactly right. Perfect. Now, from a Newman perspective, from a Newman projection perspective, let's just look at our Newman projection. So, from a Newman projection perspective, all we have to do is rotate our molecule and look down our carbon-carbon bond, and all we have to do now is draw what we see. Okay, so we have our hydrogen up top, our methyl on the left, our acetate on the right, our hydrogen on the bottom and the left, and our methyl on the right. Does anyone notice how in effect, all we've done when we attacked the backside, we've inverted our stereocenter, and now our acetate is pointing quote unquote down, while our bromine initially was up in our Newman projection. Does everyone notice how the relative position of our leaving group and nucleophile are opposite to one another? Does everyone notice that? Okay, so just to really hammer home this point, as I will have you do this on an exam, this center is R, this center is S. There's been a clear inversion of our stereocenter. And that's a key reason why the SN2 reaction is so useful, because it allows us to generate products with defined stereochemistry. Does this example make sense to everyone? Is everyone comfortable with this example? You really want to be using your models, and remember, you represent inversion by swapping your two substituents. So we will take a 10-minute break and then resume for a supplemental lecture in laboratory.